We continue now with a few funny things on BGP and how we can, that will give you a flavor of all the complexity that's possible to introduce, and it's without limit. The local pref is very often used and is very often used and is a very powerful way to signal inside the cloud what are the policies in some kind. Wait is another element that is very often used, but the difference is that it does not propagate. So the wait is another priority field, but that is used only by a given BGP router, essentially to change the decision process. The decision process is a very strict ordering of a number of criterion. If you want to do something else, then you put first a different wait that will supersede all the rest. So if you want to send all traffic in this router on that interface, which is an Ethernet one, and the other is a wireless interface, for example, that you have just in case of backup, then you use waits for this. But we will not see them in BGP announcements. In particular, they don't propagate even inside the I-BGP mesh. A very often field, a field that's very often used is also called the MED, multi-exit discriminator, which is another kind of priority. Now with the semantic that it's not like a priority field. Low means better, as opposed to a local pref. We have seen this example last week where we had ASY that had two prefixes, and that was exporting those prefixes. In one scenario, only R3 was exporting the local, each local router was exporting only the directly connected prefixes. In another scenario, each of those routers export both. The result of exporting both was hot potato routing. Now, if you want to do better routing, you can use this field, which is typically used when ASY is a client of ASX. So you would like the traffic to be carried by ASX. For example, ASY, you are a multinational company, Nestle. ASX is a company that provides you worldwide service, for example, British Telecom or Sprint. Then you want Sprint to carry your traffic. But perhaps you still have links between Vevey and Zurich that you can use, but since you're paying this provider, you prefer all traffic to go through this provider. You pay a provider, but at the same time, you don't put all your eggs into the same basket. You may still want that some of your functions work if something goes wrong with your provider. In a case like this, we would advertise with different MEDs. So we see here R3 is advertising the two prefixes, the two internal prefixes, 10.1/16 with med equal 10 and 10.2/16 with med equal 50. So the med equal 10, which means here high, which will a preferred value, is given only for the locally attached prefix. And similarly, or conversely, R4 will announce the 10.2.16, which is local, with a good value of the med equal 10. It will still advertise the other, but with a high value, which is a way to signal to X. Now, if X has to choose between the different routes to this one, he should consider the med. Let's check how this would work. Right? If we zoom on R1, R1 has received two routes to 10.2, this one. One through R3, which is an exterior BGP peer, and another one through R1 has two routes, one via R3, learned from R3, one via R4, but learned from R2 by I-BGP. With med equal 10. Now, which one will the decision process at R1 prefer? 5 more seconds. I had a turning point exception, which indicates it's coded in Java, perhaps. Okay. It will prefer, it's, okay, no, this is it the correct one? Yes, it is. No, here we are. It will, of course, prefer the route via R2, this one. And why is it so? Well, the difficulty was to locate the slide with the decision process. So the good thing about BGP is that the decision process is very well defined. Here it is, that's slide 22. The decision process tests MED before this criterion, which is the one we have seen already. We will always prefer a route that we've learned from an outside peer than an inside peer, except if the MED or also the local pref comes to change this. So here the MED is tested before. You see the importance of the MED because it's visible in the decision process. And this will in particular have the impact that packets that go to this, from anywhere in the world that go to this destination, will go to the interface R1, R3, whereas packets to 10.2 will go to the interface R2, R4. So we don't do hot potato routing. Here X will do a service for Y. It will route the packets to the point that inside Y is the closest to the final destination. This is what you expect. If you're Nestle and you get a service from US Sprint, you don't expect that when people connect to your website in the US, the traffic so if an American customer connects to a website in Switzerland, you don't expect that the traffic goes first to the Nestle office in the US and then goes along across the Atlantic in the private Nestle network, because Nestle doesn't want to have an expensive private network. So MED is typically given in situations like this, where you have a customer-provider relationship, which in particular means that X and Y collaborate. Because if X and Y are peers, for example, you could try to do that. You could say, oh, I'll pass the packets to my competitor, and I'll try that competitor to carry most of the traffic for me. But then the policy at X, in a case like this, would probably discard the MED. Would say, okay, put all the MEDs you want when I receive them. Remember, there is an input filter on any of the announcements that are received. If I receive packets from somebody who is not a customer, probably I don't care about the MEDs. We can check here, of course, that the value of this is to be able to have several routes to the destination. In particular, if router R3 crashes, for example, what will happen? Well, R1 will detect the crash and will clear all the routes that were based on the announcement received from R3. So it will clear the route that says that 10.1.16 was reachable via the next hop 111. Now, this route withdrawal will carry along all the BGP meshes, so R2 will learn about it. And now R2 will have only one route, so the decision process will have an easy job. And all traffic that goes to 10.1 will go, and similarly R1 will also have only one route, because R1 had two routes to that prefix. The one it had preferred, but the other one. Remember, the BGP database is essentially the rib-in that contains all the information you've heard. Now, what you keep as best is the only thing you use for routing, but the other one is still there. So when the route is deleted, R1 will still have the other one and will route to R2. So packets to 10.1.16 will go via 10.2. So packets from the US to the Swiss side now will go to the US office first and will be carried here, which is not desirable, but is better than not having any reachability at all. So this is the very typical use of those fields. Local pref as much as med. Typically you want to do, for the base case, a certain form of traffic engineering or policy routing, but still, since the world is so complex and there is always one router crashing somewhere in the next minute, you still want to have redundancy and other available paths here. Well, I'll skip some of the other fields that you can discuss. Other bells and whistles. One important one is this one, the so-called route flapping syndrome. A few years ago, one decade ago, there were problems in BGP due to routers that were crashing and rebooting, or BGP process crashing and rebooting. So if you have a crash typically in a process, or a fatal error in a process, it will crash. If you have a sophisticated, well-designed system, it will try to reboot automatically. That's what you would like to do in any mission-critical system. If you're unlucky, when it reboots, it will do the same, it will find the same bug again and will crash again. Okay. And you can imagine, given all the routers in the world, there must be a few that are in that state at any point in time. What happens then? When the router that has crashed comes up, it will learn a number of routes and start doing its BGP job, propagate routes around, then it will crash. Then when it crashes, all the neighbors of this router will detect the crash, will send suppression withdrawal messages to everyone, and then a minute later, this router comes up again, and the routes will change, so there will be new advertisement followed by withdrawals, etc. So it's a denial of service attack on BGP. In fact, you make that the BGP routers are constantly exchanging information that changes all the time. So the assumption of BGP is that the structure of the internet, in the sense of the AS path topology, is stable enough so that this 500,000 prefixes that are shoveled around, that they don't circulate around you and kill the router. So when that happens, in fact, the processors can't keep up. The processors of the BGP routers can't keep up with the update, and then essentially they're always out of sync, and you have loss of connectivity. In order to avoid that, so that problem occurred, like many problems in software, once the problem occurs, you're happy, it's easy to find a fix. The good thing would have been to do the fix before the problem occurs. And the solution is to do the so-called dampening function. Dampening means that when a route is withdrawn, you don't simply delete it. You keep it in your BGP database, in the part of the database that says where it came from. And then you mark it as invalid. So of course you don't use it for your decision process, but you mark it and you associate with it some kind of exponential timer that will decay with time. Now, if the route comes up again, it will receive a penalty. And if it's so, so you keep state information in the form of the penalty. If a route, here is a schematic illustration of, on the y-axis, the penalty as a function of time. If the route comes up and down several times, then its penalty will be recorded and kept, because we don't delete the route when it's removed. And it will increase above some threshold. When it increases above some threshold, you say, now I will be silent about this route. I will not propagate the information anymore. So if some part of the routes, due to failing routers, are oscillating, then you simply forget about them. You forget about them like everything. You don't forget forever. You decay the penalty exponentially with time. So after, depending on how bad the thing was, how high the penalty went, then after some time, when you go below the penalty goes below the reuse limit, you will try again. Now hopefully the router was fixed. If not, then you will discard this route again. So the effect is that those flapping routes are very quickly, after a few oscillations, are put in blackouts. They're not reachable, which means that part of the internet will not be reachable, which is bad, but is less bad than having a denial of service attack on all the BGP routers in the internet. Another bell or whistle is the private AS number. As you can imagine, there are IP addresses that are in principle public, but of course we have put aside a few of them to be private. The same is true for AS numbers. So there is a small block of AS numbers that is private. So anybody can use it to make your own private BGP network. And any BGP router that is not inside your organization will ignore those prefixes. Remember, AS numbers are not IP addresses. They are 32 bits like IPv4 addresses, but they are not IP addresses. They are used in different ways. For example, assume this could be EPFL and this could be switch. We saw that EPFL doesn't have at all an AS number because it doesn't run BGP. It uses default routes. All the EPFL routers that are connected to switch inject into the EPFL network the default route, which means the prefix 0/0, 0 bits and 0 address. They inject it into the interior routing of EPFL, which means that in order to go to the outside from anywhere in EPFL, we go to the nearest router that is able to speak directly to switch. That is a very commonly done thing. Now, if we want to do something a bit more controlled, for example, if we want to use MED, we can have both. We can not use an AS number so that the rest of the world doesn't bother about us, but we can still run BGP between EPFL. We could, this is not done, but we could run BGP between EPFL and switch here. If you run BGP, you need an AS number. In a case like this, we would use for Y a private AS number. And then the trick would be switch would hide this private AS number and replace it by its own AS number. So for the rest of the world, this does not exist. It's part of X. But this would allow to run routing between X and Y that uses all the features of BGP. In particular, this multi-exit discriminator that would allow, instead of going to the nearest point that goes to the core, to go to the best points that goes to the core. Here's another, in the category bells and whistle, here is another trick that's sometimes used. I'm showing here router R1 or R3 that sends, we have to look here to see the complete picture, that is in AS 100. And when R3 sends to R1 its AS path, it sends 100, 100, 100, 100. Right. You can think of it as a bug. This was my first reaction. But in fact, it's done in BGP. Some routers do that, and it's not considered a bug. So R1 will happily accept it. And if R1 chooses this route as the best route, when it will speak to Z, R1 will take as AS path X 100, 100, 100, 100. Now, if everything is using default configuration, there is no local pref, MED, or whatever, but just the things that are shown on the slide, which way will packets from Z go to 2111, to this place here? 5 seconds. And the correct answer is via Y. Congratulations. Well, it's just a direct application of the decision process. The decision process will choose the shortest AS path. Since this AS path is very long, there's a high chance that it's not preferred. So we will always prefer that path here. So it's another mechanism, that is another trick that is used by some systems to signal. For example, here, AS100 is signaling to the rest of the world that this link, R3 to R1, is a backup link. In principle, don't use it. I would always prefer to use that one. But of course, I still advertise it in case some things go wrong. Another important bell is the solution to the I-BGP mesh combinatorial explosion. We said that in BGP, inside an interior, inside a domain, all BGP routers have to be directly connected over TCP connection. I should not say directly connected, have to be connected over TCP connections and are BGP peers. They are not on link, not necessarily on link, but they are BGP peers. That's what we call the I-BGP mesh. Now in the lab, there will be no problem. Inside, in GNS3, we'll ask you to do meshes with 3 routers, so that will be okay. Imagine you are US Sprint and you have 50 backbone routers. Every of the 50 routers have to have connection to 49 other routers, which may be okay, but may also be considered too much work for the routers. So if your network grows very large, perhaps 50 is not large enough. If your network is much larger than 50 BGP routers, plus remember, we run BGP typically everywhere in our network, just because we don't want to do redistribution. So sometimes you have larger networks. How can you solve the problem? Well, as usual, the difficult thing is to recognize the problem. Well, one way to solve the problem is a bit ironical, but it consists in using E-BGP as an I-BGP, or more precisely, to do what is called confederation. So this is a private domain which has too many routers to do a good BGP mesh. I mentioned too many BGP routers. It may be also that you have expensive links. For example, some of your routers are in America, some others in Europe. So you don't want that all routers in Europe send all the information they have to all routers in the US. You want to compress a bit the traffic that goes across the Atlantic. Right? So one easy solution is to treat your network as a collection of separate domains. And you can do that easily by giving private AS domains here, and it is called configuration. So you would have an AS P1, P2, and P3. And inside each of those local subdomains, if you want, you use this AS number and you run the E-BGP protocol inside your domain between routers, but it's E-BGP because they are considered to be between 2 routers that are not in the same BGP domain. Of course, you need a little exception to all the rules we saw. Those private AS numbers need to be changed to your true AS number when you talk here. So on this interface, you will need to configure this router to change all the P1, P2, P3 that it has everywhere by the value Z, which is not a very big thing to do. And that easy trick solves everything. Right? So we will have, so the only thing that's difficult is to understand what people are talking about. We will run E-BGP using private AS numbers inside a single domain. But other than that, it's business as usual. There is an alternative to that, which is perhaps cleaner from a terminology viewpoint, but is essentially the same. It's called route reflectors. Route reflectors are essentially the same, but is an alternative solution. that is sometimes preferred, which essentially avoids the use of E-BGP and private ASs. So the terminology is a bit different. What I don't like with route reflectors is that it contradicts the principle of parsimony, which says that if you can do with less, you should do with less. So with this, we do with less. So it's better, but both are used. Sometimes also you have a similar problem with E-BGP. In all the figures we saw, you had domains that are clouds that are connected over a single link to a few other domains, but sometimes the interconnection is different. If you're in an interconnection point, like May West, May East, the most common ones, IXC in Zurich, where you might have hundreds of providers that connect to each other, then you have a similar mesh problem. So anybody connects to everyone. That makes a lot of connectivity everywhere. So you do a similar thing, which is called a route server, where instead of having everybody speak to everyone, everybody speaks to a mailbox in some sense, which is a variant of BGP that we won't see in detail here. A few more relaxing slides on BGP for real here. So here are the external connections of our switch network. Switch is a small network worldwide, right? But it has very high performance links because of, for example, CERN, that is connected with very high performance links to all other research networks. And as you see, it has connections in Geneva, in Basel, in Zurich, also in the East Switzerland and in Tessin. SWIS6 is one of the interconnection points, so if you want to become an ISP, you will probably need to connect there. As you can see, it's cheap. This is the AS number of switch, and this is if we do the graph of all the neighbors seen from switch. In fact, we say from EPFL, but from switch. Here is a snapshot taken some time ago, and that shows the graph of connectivity. The characteristic of this graph is that the degree of practically all nodes is very high. So you see that switch is connected to a large number of ASs, and this is quite typical. So it is, the idea with BGP is because it's self-organized, you cannot trust on interconnection of one with one neighbor to solve your interconnection problem. This is the same view. Some statistics that were collected 2 weeks ago. I give also the sites where you can find them. On the top is the number of IPv6 prefixes in the core networks of the internet. You see that we're above 500,000. In the bottom is the number of ASs, autonomous systems. This number itself is large. And this is also why there's an incentive to all companies that don't need ASs not to use them. And this is the growth curve of IPv4 prefixes since the beginning, not the beginning of the internet, but almost the mid-80s. Well, TCP/IP were invented in 79, BGP4 a bit later. So we see that at the happy years, 94 is when the internet went public in some sense, when Mosaic Netscape became important. We were at 10,000 prefixes. So the vision of the problems was completely different at that time. And then we had the internet bubble that blew up at that time. We see a little stop in the progression. And now it continuously increases, and China will take care of making it even bigger, and India. So we're at 500,000. IPv6 is much more modest, so the scale here is 20,000, right? Not 200,000, it's 20,000. The story will tell where this curve will go. Is it exponential? Is it linear? Well, that's another topic for another course. And we'll come back in 10 years to see. Voilà, that's it for BGP. Any questions? No question. Then the next topic is an apparently simple one, which is the application layer. F5. Well, it's simple because the work is not in this lecture. Of course, most of the development and the complexity of the internet is in the application layer. So if you want to do Facebook, you need a lot of programming, perhaps not at the beginning, but just to run all the servers. But what we will see is, in particular, the relationship with IPv4 versus IPv6, because the application layer has to do with the transition and interworking with IPv4 and IPv6, which will force us to talk also a bit about application layer gateways. So in this course, in principle, we don't talk about the application layer. You did an application layer that was in the lab on programming. You did a little program that sends secret keys and messages, unicast, multicast, TCP, UDP. So you did an application. So the application layer is about things like this. But of course, the specific application layers like the web are not the topic of this course, but we find typically it's useful to see the things we find in any application. We typically find a protocol and a format. A protocol is the rule of the game with the interaction. If you remember, a protocol in the layering approach of TCP/IP is the rules of the game between two entities that are at the same level in the layered model. And the format for documents. When you do an application layer, typically you use TCP or UDP. There's no other choice. You can build intermediate things on top of TCP or on top of UDP, but typically you will need to use them. Let me skip all this. That is quite common. It's important sometimes to understand how an application uses TCP or UDP. I mean, you should get a feeling for that after the labs we did. Here is an example. FTP, File Transfer Protocol, which is a bit obsolete, is replaced by secure versions of it, and was primarily obsoleted by HTTP, which is another file transfer protocol. FTP, in its original version, uses the diagram on the top. When an FTP client, when you FTP to a remote machine, you open first a TCP connection that is used for control. You send commands like ls, change directory, remove a file, etc. So this is done over a first connection. And then when you decide to do a file transfer, FTP will open another TCP connection. And here it will open the TCP connection from the FTP server to the client in the regular FTP mode, called active mode. In the passive mode, it opens it from the FTP client to the FTP server. Why do we have both? Well, the first one was the first originally developed. The second one is the only one that goes through firewalls today, so it was needed to avoid firewall problems. Little quiz. Which of these port numbers are TCP server ports? You have to look on the left here. Five more seconds. Ha. So we have so let's analyze. So we have 3 ports essentially, 20, 21, and 1, 2, 3, 4, 6. Is 20 TCP server port. A TCP server port is a port on which we do listen and we wait for TCP SYN packets to arrive. If you look at port 20, which is reserved for FTP, it's not waiting for a SYN. It's waiting for a SYN ACK. Right? So the connection is opened from the FTP server side, and the server port in that instance is, in fact, 12346. Right? Now, of course, the same port is used twice. I admit it's a bit mean. But if I look at the top, the red 12346 versus 20, the server port is the 12346, the TCP server port. This one. This one is not a server port. And 21 is a server port. It's waiting for somebody to connect. So the correct answer is number 6, with a very small minority here. So this is just illustrating the difference between server port and reserved port. Usually they are the same, but in some weird case like this one, it's not what is happening, right? And in order to know what is happening, you have to understand the logic of the application. Let me skip this one. So that's all we will say in general about the application layer. One application layer is DNS. We could view it as network control, but in fact, if we follow the layering of TCP/IP, we can transport IP packets without DNS, if you know the IP address of the destination. So we really have to think of it as an application layer. Of course, it's an application layer of a special kind that provides a service that's required for the rest to work. As we know, DNS maps DNS names, such as this one, to IP addresses. So DNS is constantly evolving the set, but it's organized in the following way. There are so-called a root. It's organized as a structure. Now the set of names is organized as a tree, with at the top of the tree, in principle, 2-letter things, CH, FR, DE. Those are countries. So anything in 2 letters is a country. Even if it's called LI or whatever, it means it's a country. It's Libya, for example. So it's often used to make nice looking URLs, but it's always a country. The 3-letter top-level domains were the original domains that were done when the internet was created. .com means company, .org means organization, the ITF, the ITU, things like this. MIL means the US military, gov means the US government, edu means the US education system, etc. That is what they mean originally. Of course, now anybody can use the names like .com, certainly not .edu. You have to be a US university. And then, more recently, if you have enough money, you can buy any name. Nestle, your family name, will cost you probably $500,000 per year. But so that was very, very recently added. Then we will see also a special domain in 4 letters called ARPA that we will mention a bit later. It's also possible to, so here you have to do code division demultiplexing to be able to read this. A few years ago, some of your predecessors had opened a website called epfl.ch. They were Swiss German. So it's the way of pronouncing EPFL in the French way, but written the German way. So that is possible now. It's possible to, so on this website, there was pre-Facebook. There were all the texts of all the exams with the solutions given by the students. And teachers could not log on there. I guess you have the same on Facebook now. Yeah. So now it's possible. So originally, all of that, of course, was Anglo-Saxon, American, to be more precise. So the alphabet that is used is the English alphabet, and it's still true. So all these DNS names have to be in this reduced set of characters. But there is a mapping with a very interesting code called the Punycode that translates this into that. So when a DNS client receives a request for something like this, the first thing it will do is translate it into something that will be coded with the classical characters. Now in this specific case, EPFL will be xn-pfl minus rna.ch. So this is how it is used. Now, how does it work? When we type in something that contains a name rather than an IP address, as we have seen, we have a client, a DNS client in the machine, in any machine, in your iPhone or smartphone, in your PC, any machine. The first thing it will do is use a piece of code called a DNS client. That may be a system service or may be specific to the application that will go to a DNS server, will send a query to a DNS server, like here when Lisa clicks on www.zurich.ibm.com, then the machine will send a message, number 1 on this cartoon, which is a DNS query. It is an application layer message sent over UDP. DNS uses UDP. And inside the UDP datagram, there is some text written in English with things like, I am a query, RD equal yes. RD means recursivity desired. So that we'll see what that means in a second. And the question. The question is www.zurich.ibm.com, capital A. Capital A has to do with the list of records that are in the DNS servers. The most important records in the DNS servers are the capital A records. Capital A stands for address. In fact, IPv4 address. But there are also IPv6 address, which are quadruple A, 4 times A, because an IPv6 address is 4 times as big as an IPv4 address. So here, this PC does only IPv4. It asks for an IPv4 address. The server is recursive. Recursive means that it will try to solve the query completely. Most servers are not recursive. If you go to a Google server, it will not solve the query completely because that gives a lot of work to the server. But that's what is done if you access the EPFL DNS server, 15.7 or 15.8, and your IP address is inside EPFL. So typically it's a service you provide to your customers. It's not a service you provide to anybody. Here, what will the LRC SUN S, which is DNS server, which is configured in the PC, remember, with DHCP or whatever, the PC needs to know what is the DNS server IP address. Now the DNS server receives the query and it doesn't know because EPFL is not IBM. It doesn't know what's the address. So what will it do? Well, it will go along the tree, the DNS tree of names, and it will go, if it doesn't know anything, as we will see, very often we don't go the full process. We cache what we know, but if it's the first time this server has a question of that kind to answer, it will go to the top of the tree. So it will go to one of the 13 so-called root name servers, which are name servers that contain the bootstrap information for all the top-level domains. So inside the root server is, for example, the IP address of the DNS server of IBM. So the message will go sent by EPFL to the root name server. Now, this root name server works in iterative mode. It will not completely solve the question, the answer, the problem. The problem is find the IP address of www.zurich.ibm.com. But the root server knows, oh, that's ibm.com. I will not give you the answer, but I will give you the IP address of the ibm.com DNS server. And the response will go back to the EPFL server. Now the EPFL server will continue and will send number 4, the same query, to the IBM server. And now the IBM server will answer. So number 3 was the answer from the root name server that contained the IP address of a few IBM servers. So the root name server, as we can see, they don't contain all the information. All they contain is the information about the level that's just below them, which are what are all the IP addresses of DNS servers of the level just below the root. And then hopefully the IBM.com server, which in that case is Watson, will know the answer and will give the response back to Lisa, who can now click. Who has clicked already, but during all that time nothing has happened. So you see that the web page is loading, but nothing is happening. This thing is being resolved. Voila. The suspense goes on. We will see how things continue next week.